Hello, everyone. Welcome to the sixth and final day of the Environmental Research 2023 conference, also known as the Infrastructure and Sustainability Day. There are 3 sessions today, and this is actually the last one. So I just wanted to remind everybody that we have a wonderful journal that is the home of infrastructure and sustainability research. It's Environmental Research, Infrastructure and Sustainability, a sister journal of Environmental Research Letters. And so today's speakers were sponsored by and invited by the journal, and several of the speakers are on the editorial board. I hope you enjoyed the other sessions, and we welcome your questions. Today, we have 5 wonderful speakers set up. My name is Arpad Horvath. I'm a professor of civil and environmental engineering at the University of California, Berkeley, and also the editor-in-chief of Environmental Research, Infrastructure and Sustainability. Our first speaker is Jukka Heinonen from the University of Iceland. He is a professor of sustainable built environment at the Faculty of Civil and Environmental Engineering. And his main fields of research are consumption-based urban carbon footprinting and low-carbon urban settlements. He has developed research approaches and analysis methods specifically for modeling the indirect and outsourced emissions from the built environment. Jukka, the screen is yours.
Thank you, Arpad, for the introduction. Nice to be talking to you today. So I will be talking about the built environment embodied emissions today, and how I think that we don't necessarily pay enough attention to them. And I will be happy to continue the discussion then afterwards. Hopefully this provokes some thoughts. I will start with this relatively old study from Miller et al. From 2013, in which they estimated that if the lower development countries would catch up with the amount of infrastructure per capita compared to what we have in the most affluent countries, this would cause emissions of around 350 gigatons in different greenhouse gases. And now, even if this would kind of be an abstract number otherwise, then when starting to compare it to the carbon budgets we have left for different levels of warming, we can basically see that this amount alone equals to the budget, basically what we have left for 1.5 degree warming. And this graph here, you can see it's the green one, and it shows the 50% likelihood of not exceeding 1.5 degrees warming. So basically, we talk about amount of emissions that entirely is enough to just entirely eat up the whole carbon budget we have left for 1.5 degree warming, if only these lower development countries would catch up with the amount of infrastructure per capita. And then at the same time, when looking at what happens in the most developed countries, is that it's not like they would have reached some kind of a saturation level beyond which there's no need for additional infrastructure. Somehow it looks like that the amount of construction is kind of just increasing, and we are sort of just now hiding that development behind the sort of general idea of developing a future sustainable built environment, but without kind of thinking this aspect at all, and sort of like starting to assess the emissions from the point when we have a new infrastructure system in use, whatever system it is in question. What that has led to is, of course, that all kinds of construction materials are being produced to higher extent than ever before. And I just very recently saw a nice, like kind of an illustration of what this cement production, for example, what this means if you try to illustrate it in some tangible way. And there was a journalist who calculated these numbers, and according to his calculation, if you produced a kind of typical 30 centimeter pillar, concrete pillar, then this amount of cement production for that concrete would be enough to produce a pillar from the earth to the sun each year. Or if you put it in a thin line, then you would need to produce it with the speed of light to just give a little bit of perspective to what this means in such numbers. And to me, it's kind of it means that when we look at each different sort of conventional key material that we most use in the built environment, and we see a very similar curve in terms of how much it's being produced, then overall that either there is not much consideration for the sort of future sustainable built environment, or we consider it in a pretty wrong way. There is one sort of underlying issue that I want to pay a little bit attention to, which is that I see that more and more the construction industry, at least like in the context where I work, which is most of the Nordic countries, that these environmental or sustainability certificates for buildings, that they are gaining more and more attention, and they are becoming more and more important kind of drivers for the future, or like transformation of the sector, the industry sector overall. And to me, it sort of looks like that this like a green transition is more like some kind of an illusion of such transition than an actual transition. And this has a lot to do with the fact that these certificates pay very little attention to these embodied emissions and to the pre-use phase overall, which then leads to kind of a false image of a transition that would be ongoing in this sector. This is a relatively recent paper of ours in which we talk about this issue and actually show that this indeed is the case. And what this leads to is basically an idea that almost kind of the same buildings, what we used to have, then suddenly with one of these labels, be it BREEAM or LEED or one of them, then becomes sustainable or somehow green building. This is a good example of such a building in Iceland on our university campus that advertises, or that is advertised as a sustainable building and some kind of a good example of where we can go when we pay attention to sustainability when building new. But at the same time, just by looking at it, it's easy to understand that there is not very much that is sustainable in it. And when I discuss with people who construct these buildings, then many of them, what they say to me is that basically they do exactly how they did things before, but with some additional paperwork to obtain the certificate. In the Nordic countries, mostly, particularly in Iceland, the use phase energy doesn't really have a lot to do with the overall life cycle greenhouse gas emissions, whereas the pre-use phase, of course, it has exactly the same impact than elsewhere for the most part, and particularly because Iceland is importing everything, then it easily also falls out of any accounting for the emissions, but can be that it's even higher emissions that is associated with the pre-use phase than in many other locations. And overall, I see the same kind of, that was one example, but when looking at how this like future so-called sustainable built environment is created, it somehow gives a feeling that this aspect of the importance of mitigating climate change has not really been either understood at all, or we have kind of just pushed it aside because of these guiding systems like the green building certificates don't really pay attention to that, or that when we look at, for example, city level accounting of emissions or even national accounting of emissions, construction materials easily fall out from those assessment schemes. These both are from the capital region in Finland, in which kind of it's has been very strong guiding issue that sustainability from different perspectives is taken into account. But when looking at what is happening is that not really anything very important is changing in terms of how much emissions we cause to develop this future sustainable built environment, which basically means that it narrows down to issues related to, for example, transport systems, which of course it's not like it's unimportant, but in a recent quite interesting assessment, one of the middle-sized cities in Finland, the city of Tampere, they included for the first time construction materials into their city environmental assessment or greenhouse gas assessment of the city. And whereas they had always considered that it's transport that is kind of by far the most important factor for them, and then building energy use after that, they noticed that construction materials, if included in such an assessment, on an annual basis lead to almost an equal amount of emissions than transport in its entirety. And I heard from many of the city people that this was quite eye-opening for them, this exercise, but also it tells that really it has been missing from this level of planning and assessing the emissions. And at the same time, it's these green building certificates that are getting more and more attention and becoming kind of stronger and stronger guides for the development of the sector. And then it sort of means that instead of this pre-use phase part becoming better recognized, it's even less recognized all the time. This is a study that the Green Building Council in Iceland conducted. Here is a pre-am building versus a conventional building over its lifetime. In the Icelandic conditions, the operational energy part doesn't really play a big role, and actually it's projected to play a smaller role all the time, because even the very low current emissions from renewable production will be significantly lower in the future because of carbon capture technologies that are being installed as we speak. So it means that the vast majority of all the emissions, it comes from the pre-use phase, which is the lowest block in this illustration, and overall the difference between these two buildings is almost non-existent, and focuses on the energy use, which in the future will play even smaller role. And here you can see how it is when put on a timeline, comparing the pre-use phase here as kind of the initial sort of carbon spike from these buildings, and then the use phase over time. And as you can see, the emission intensity of the energy system in Iceland is really low, and will be a lot lower in the future, even after this carbon capture system is in place. And now we come to another kind of important issue, in my opinion, which is that we tend to calculate the emissions in the built environment related to different built environment systems as if they all happened sort of at the same time in the beginning of the lifetime of the building, or we divide everything as like a annual equal load, whereas in reality we have these high early life cycle emissions, which typically mean that they are, even in conditions where the energy grid would be much more greenhouse gas intensive, this is an important amount in comparison to the use phase, where emissions then happen sort of slowly over time, and or accumulate slowly over time. And then I will come back to the end of life later, but when we also calculate the end of life here, using the technology assumption of today, then we might end up having really kind of misleading results, which would put conventional materials as kind of the preferred option in some cases. In Reykjavik, this is one of our pretty recent calculations for the city of Reykjavik, in which we compare the different life cycle stages and the emissions from them. And in Reykjavik, which is in global terms a small city, 150,000 inhabitants around, but the construction activity is high and the city is growing fast. And what we calculated is that currently the emissions related to the construction of new buildings is almost as much as the energy use of all the buildings in the city. And also then when looking at the future projection in terms of how much the city will grow within the next 10, 20 years, we talk about emissions of around 2 million tons of greenhouse gas or CO2 equivalents from just this one small city. This is quite a big greenhouse gas commitment by a city that is to be, according to their own target, that is to become carbon neutral at around the same time than they are causing these 2 million tons of greenhouse gas emissions. And this is not at all included in the city accounts, nor really recognized by the city, of course, now hopefully by some people after our calculation of it. This is from relatively well-known Jurkina et al. Study from a few years back, in which they show how the alternative could work. Now that we talk about kind of our sort of linear business model and that connected to the built environment and the building sector, then what we have so far achieved is that we have kind of transferred from the below ground stored carbon into the atmosphere, where buildings and other infrastructure systems have been one of the sort of key vehicles in that. Whereas if we would want to see the built environment from an entirely different perspective, so that it would have a really different function in our climate change mitigation, not just one where we try to kind of solely improve the built environment so that we are causing less harm, but look at it as something that could be really part of the solution and part of the long-term balance or sort of returning to a kind of acceptable balance, and then maintaining that the built environment overall could play an important role in it if we started looking at it from the perspective that we would actually again start transferring the atmospheric CO2 or greenhouse gases to below ground and built environment storages, where it would then be stored over a long period of time. And then when we reached such a situation, such a kind of balance, then that we would have like a carbon neutral circle that would then maintain this balance over time. This would require kind of an entire paradigm change in terms of how we see the built environment, but at the same time, we can already, with the knowledge we have now, we can basically say that it's possible if we want to do that. This is Amiri et al. Study from a few years back, in which they looked at different building LCA calculations that have been published in academic sources, and found that it's relatively high number of them that has found or that have found that the stored carbon in buildings using plant-based materials can be more than the emissions caused by those same buildings. So basically this means that on a building level, we can reach this kind of a positive balance. And going beyond, this is a very recent study from Talvitie et al., in which they took like a step beyond from this Amir et al. Study, looking at a comparison between typical forests and cities that would utilize their buildings for storing carbon, and found that the carbon stock of a city can reach the same level or even beyond typical northern forests, which is quite interesting and an important signal for this paradigm change to be possible, or like the result of such a paradigm change to be exactly that the built environment could be an important vehicle in kind of returning to such a carbon balance that would then be the desired outcome of our climate change fight. And so far, we have basically been only looking at buildings. But of course, buildings are only one, of course, important, but still just one of the infrastructure systems we could utilize for storing carbon and for creating this positive circle of sequestering and storing carbon into the built environment and making it neutral, of course, first, but even sort of carbon positive, so that it would be storing all the time more carbon than is caused by the built environment, and then overall over time allow us to kind of convert this pattern what we have been in the middle since the beginning of the industrial era, that we are sort of transferring carbon from the below ground sources to the atmosphere, so the built environment could be one that changes the direction. We have a lot of opportunities related to all kinds of materials that we utilize in the built environment. Overall, of course, we might want to get rid of our somehow very strong will to pave everything, but starting from, of course, buildings I've already covered, but then different pavement materials, we could utilize materials that store carbon. We could utilize all kinds of living structures that improve the carbon balance and bring in the sequestration aspect as well. And then when we start moving from buildings, where it has already been shown that we can find ways to store more carbon in the buildings than what is caused by those same buildings, then when we start thinking about all surfaces that we have in the built environment and look at them from this kind of a perspective, we could reach such built environment or such a built environment that it would be significant amount of carbon that it could be storing in comparison to, like, more carbon in comparison to what was caused or what is caused over time by the same built environment. So far, these are just individual examples, like here on the left-hand side, and the reality on the right-hand side is what we typically see when looking around in our different built environment contexts. I will end here. Thank you. Hopefully, I can answer some questions for you.
Thank you very much for your presentation. I'm not seeing any questions in the Q&A, but let me ask a question about the end of life. You made very important points about carbon positive buildings, but there seems to be a concern that there is an end of life problem with plant-based materials, and some people might even believe that that leads to higher life cycle emissions than with conventional materials. Could you please unpack this a little bit and explain what you think about this?
Yes, I run into this amazingly often, even if it would kind of seem to be very straightforward that conventional materials must be worse option than plant-based materials. But sometimes I see such calculations in which the end of life has been calculated as extremely high emission phase for plant-based materials, because of, for example, combustion of these materials in the end of life. And it might even lead to the conventional material option showing us as the preferred one. And in my opinion, this doesn't really make much sense, because we talk about either very early life cycle emissions as in conventional materials when produced, which inevitably are there and lead to warming ever after when emitted, in comparison to emissions somewhere far in the future that are pretty uncertain to begin with. In my opinion, we should not be calculating emissions potentially taking place in 2070 with the same technology than we use today for the same life cycle phase. And then as another aspect, we are talking about the consequential impact when we talk about combustion. So even if there would be combustion, then it doesn't happen for just combustion. That's a little bit of another issue, but just the thing that we talk about certain emissions early on or highly uncertain emissions somewhere far in the future, that leads to, in my opinion, a conclusion that we should utilize some kind of a discount factor in built environment LCAs when we talk about systems that have very long lifetime. We, of course, everybody knows that we use discount factors in all economic accounting when it somehow covers longer time period than basically 1 year. But in LCA, we don't have such a system. But in my opinion, when it comes to built environment context and built environment systems, then we should have, because that's one way of tackling these like highly uncertain future emissions compared to current emissions.
Thank you. And even if we didn't apply any discount factors from the charts that you have seen and in previous papers, you're showing that the current impact is just so much higher that even if we don't believe in discounting of carbon, the evidence is overwhelming that we need to look at carbon sinks right now. Thank you for that. Sort of a follow-up question to this then is, of course, some countries are more fortunate to have the plant-based resources for construction materials than others. But in general, wouldn't the increased use of plant-based materials lead to reduced forest sink capacity?
Yeah, kind of unfortunately, we are like maybe 100 years too late in this transition. If we started 100 years ago, then we could right now have like a really very well functioning circular system in which forests are again storing the same amount of carbon than before kind of starting this cycle of storing more and more carbon to the built environment. But even if we started it now, of course, it doesn't need to be that we cut down all the forests that we have and then wait for the next decades for them to grow back. I don't think that the transition to plant-based materials can rely on just one material. It will be several different materials, even quite a high number of different plant-based materials that should be utilized, and some of them actually have relatively short life cycles on their own, like bamboo and such materials that are fast growing and don't have this problem of like particularly northern or far southern forests, with which then the logging of these forests, of course, leads to decline in the sequestration capacity for quite a long time. But still, at the same time, of course, if done wisely, then we are storing the carbon that we have in them, and then we are losing some of the sequestration capacity for some time. But it doesn't require that long a time before we enter a phase in which it is positive overall for its impact.
Thank you very much for your answers and the wonderful presentation. We're going to transition to our second speaker, Professor Matthew Eckelman from Northeastern University in the Department of Civil and Environmental Engineering. His research interests include life cycle assessment, urban energy and emissions modeling, and sustainability of urban infrastructure. Professor Eckelman.
Okay, thank you very much, Arpad, and it's a pleasure to be here with you all. I'm speaking to you from Boston in the United States, and I'm going to focus on more of a building design perspective rather than only the building materials, because of course all these materials we are looking to be low carbon and low environmental impact. They work together. They have to be synergistic in an overall building design. I think we all recognize buildings are a very large piece of the puzzle around decarbonization, and especially when we're focused on building materials specifically, it looks like about 10% or so of the overall global greenhouse gas emissions comes from the production of these materials. And because of this recognition and the ecosystem we're in, the innovation ecosystem we're in, there are a lot of very interesting innovations happening right now to try to develop low carbon materials, low carbon iron, using different types of bio-based reductants, completely carbon-free steel. This is a plant going up in Sweden. Low carbon concrete that you'll probably hear more about today, various technologies for that, and even low carbon aggregate. So this is a company here based close by to me that's making foamed glass aggregates, very lightweight aggregates out of recycled glass. So actually, I'm very optimistic about the technology landscape that we're seeing around low carbon materials. But those materials have to work together in a building. And so some of the research we've been doing, some of the inquiries have been to look at whole buildings, not comparing building materials, but comparing materials in buildings. So we took a look at 4 iconic buildings in different parts of the world. The upper left one in Spain, almost fully concrete building. The Wood Innovation Center in Canada. Highly steel building in the lower left-hand corner. This is in Salt Lake City in Utah in the United States. And fully masonry building down here on the lower right in Austria. And one of the kind of basic questions that we have in this space around environmental assessment of building materials is, which material should we build with? Which material is going to give us the performance we want to make beautiful structures that are high functioning, high performance, and also as low environmental impact as we can get. So we did a kind of typical life cycle assessment. We looked at the building construction, and we found, of course, a big difference. The masonry building is very heavy, as is the concrete building. So you see global warming emissions per square meter, that kind of typical values that you would expect to see, including the wood-based building down here in the bottom, slightly better than typical construction, which is mixed material. But the insight we were looking for wasn't just the construction side. We wanted to see how these different types of buildings play out over long periods of time. And as we extend buildings to a long lifespan, not just a kind of 60 or 70-year default, but a much longer lifespan that we would hope to see for a high-quality building, the impact of replacing poor quality construction or construction that doesn't have a use, it's not a building that people want to keep around, it doesn't have a way to reuse it very easily. The typical construction graph you can see gets larger and larger, far eclipsing any of these other buildings, which are designed in a way to be adaptable, to be reusable, and to have a longer life. So the idea here is, regardless of what building material we use, there should be a focus on longevity. There should be a focus on not just the architectural design, but also the structural design around longevity and keeping these buildings in service for as long as possible. Now, on the existing building side, we call this adaptive reuse. And this is a picture you're seeing from my city in Boston. This is down by the river, or down by the harbor rather, place called Russia Wharf. This is the place where all of the business that the Port of Boston used to have with Russia centuries ago came through. And this building has been used for many, many different purposes over the years. And architecturally, it has features that allow it to do that. So it has lots of windows, high windows, open space, pretty high floor to ceiling heights. So you have spaces that can be used for a lot of different purposes. So we have a sense of what kind of features we're looking for existing buildings. And now we want to take that kind of ethos and apply it to new buildings. How can we design new structures and take advantage of the structural engineering innovations that we have to really get buildings that are high performing and long lasting? So this is a project that we have from our US Department of Energy to look into this issue. Some of you might ask, well, why are we asking this at all? Why don't we just build all wood framed mass timber buildings everywhere? Problem solved. We'll just sequester all this wood in our built environment. And this will help not only with the carbon storage problem, but with also reducing those emissions associated with building materials like steel and concrete that we know to be very important. And there have been many great strides in the mass timber building industry. You're looking here at, I think to date, the highest mass timber building in the world, which is in Milwaukee. It's about Milwaukee, Wisconsin in the US. It's about 25 stories high. And every year, I feel like we see larger and larger buildings here. So that's a really wonderful progression. But when you look at the market portion, how much of the market does mass timber building have? It's very, very small. One of the reasons for this is that the current ecosystem for architecture, engineering, and construction, the AEC sector, it's focused around traditional materials. And people who work in this industry are typically very conservative. They're cautious. And it takes a while for them to become comfortable using new materials like mass timber, for example. So we want to find a way to harness some aspects of wood and also take advantage of the existing ecosystem around steel buildings. So what we're trying to do in this project is to find a way to move from this traditional, let's say typical steel frame building with cast in place composite floors, so concrete on steel deck, which has major issues for greenhouse gas emissions. The floor slabs themselves, if you go up to a typical mid-rise or high-rise building, the floor slabs are typically more than half of the embodied carbon of the building. In addition, pouring that concrete takes a long time. It has to cure, and that slows down the construction process. And it's very difficult to reuse these kinds of materials, especially these composite floor systems. So what we're trying to do is look at same steel frame buildings, but using all cross-laminated timber panels, so wood-based floors. And it turns out these have lots of big benefits for the environment. One is we move away from all that concrete, so we're using CLT. This helps also with sequestering carbon. You can put these panels into place very quickly, as I'll show you in just a second. And we can design the connection structurally between the steel and the wood flooring system so that we can enable design for deconstruction, or DFD. So here's a picture of one of those CLT panels going into place. Typically, the length of these, you can see up to 50 or even 60 feet long. Okay, so in our US units anyway. This is could be longer, except the trucks have to be able to turn around corners and deliver them. But that's really the only reason why they couldn't be a little bit longer. And you can crane these into place. The truck shows up. In about 4 hours, you can unload all of the CLT panels and crane them into place and attach them to the steel frame. So the construction time, this knocks weeks off the construction time for a building, which is, of course, very attractive to the construction firms and the owners. Now, one of the problems here is that we don't have a developed industry around CLT here in North America and the United States in particular. Almost all of the CLT comes from the Pacific Northwest. You can see this dark green area along the Pacific, or in the Southeast, the US Southeast. But you can see here where I am in the Northeast of the country, there's actually quite a lot of forest resources. And we're not using them. And there's also not much manufacturing. So if we wanted to have a CLT-based project, a wood-based construction project here in my part of the world, we would have to import CLT perhaps from all the way across the country, the United States or Canada. We might be able to import some from northern Quebec up in the north of Canada, or very frequently we import CLT from Austria. So we have some transportation emissions from that, and also we're not taking advantage of the bio-based resources that we have. And there are some beautiful forests that had been used for many years for pulp and paper, which that industry has really declined in my part of the world. And so these are forests with a lot of available wood that aren't being utilized. So the idea here is maybe we can use some of this local material. But of course, we need to test it. We need to look at how it performs in strength tests as just regular material. This is part of the project. We're looking at these new types of woods to see how suitable they are to include in CLT and other wood-based building products here in our part of the country. We're also producing our own CLT and looking at planks, how planks perform structurally. So we're basically putting a lot of force on these planks and seeing how they delaminate or how they crack, and whether they can be put into place in our buildings. This testing is a really important part of innovation around low carbon building materials, because without this testing, the structural engineers and the architects aren't going to be comfortable using this material, and the material won't be written into building construction standards that allow its use. So this is a really fundamental aspect of getting more wood into our buildings. In addition to the material testing, we're looking at a whole building level on how this will perform in a whole building life cycle assessment sense. So we are modeling some different building types, low-rise buildings and high-rise buildings. The requirements for wood that you put into these are pretty different. So low-rise, there aren't actually a lot of requirements. You can very liberally use wood-based building materials in many different ways. But for high-rise, there are more strict building codes around things like vibration or acoustics or the spread of fire, and also how you design, for example, for seismic loading or wind loading. So we designed a few different prototype buildings, one set in the west where we have more seismic activity, one in the east where we have more wind-based loading that we have to worry about. In addition to that, we've played around with different structural systems. So what you're seeing in the kind of top structural design here is just a very typical system where you have a standard bay width. So this is, I think, 30 by 30 feet wide bay width. But because those CLT panels are so long, actually they can go across multiple bays. This is something you can't do with cast in place concrete. So instead of having these steel beams in every bay, actually we can get rid of a lot of the intermediate steel and just put the long 50-foot or 60-foot CLT panels right over 2 bays. And this has major benefits, actually. So we've used some very typical life cycle assessment software coupled with building information models. This one is from a software called Tally, which is a plugin for Revit. And you can see when we measure the tons of carbon dioxide equivalents of this building, both the steel and the CLT, even just the baseline building, okay, which is the one in the upper diagram there, we're seeing negative emissions. So as long as this building is in service, we're taking advantage of that carbon that's sequestered in the CLT. But if we can get rid of even more steel, and we have to increase the width of the CLT in order to provide enough structural support, this stretch design, which corresponds with the lower structural pattern that you see, gives us even greater carbon sequestration. So by playing with the structural patterns, by making sure that we are designing to code, but still optimizing for low carbon materials, we can achieve really fantastic levels of carbon sequestered in the building itself. This is only one half of the puzzle. The carbon sequestered in a building doesn't help as much if the building doesn't last a long time. And you heard about this from the speaker that came just before me. So another really important part of the work in this project has been to design structural systems between the steel, so the steel member that you see here, the I-beam, and the CLT, in a way that we can actually remove the CLT and the steel, both of them, and potentially reuse them. Take the steel member and the CLT panel, and after deconstruction, put them in a completely new building. We're seeing this more and more, especially with steel, but so far, this hasn't really been a feature of CLT. Mostly because in order to meet acoustic building codes, we pour a bunch of concrete or gypcrete on top of the CLT panel, making it really difficult to deconstruct in a way that doesn't damage the panel when we take it out. So the idea here is to find these structural systems, test them in a very large laboratory where we build one of these buildings to scale and then shake it until it essentially fails. And we design a system that maintains the performance and allows us to reuse these CLT panels afterwards. We're trying to understand what the benefit of this is on a life cycle basis as well. And the results we see are very encouraging. So if we take a look at some different building sizes, what you're seeing here is 3 groupings of results for different floor thicknesses and bay widths. The traditional building is in the left, and you can see most of that carbon has to do with the production of the building materials. If we go to these DFD systems, these designed for deconstruction systems, it does take a little bit more material. Okay, we need a little bit more steel. We have to be careful about how we clamp things or use this new interesting innovation called densified wood to spread the load across a larger portion of the panel. But if we manage to reuse either the steel or the CLT even once, you can see that one reuse result is worth it. It's better by far than the traditional building that doesn't have designed for deconstruction. And if you can reuse even more times, you get an even greater benefit. So having visibility on both sides of this problem, first of all, getting carbon into buildings as much as possible, as fast as possible, taking advantage of the existing steel ecosystem to push wood hybrid steel CLT buildings on the one side, and then keeping the wood in those buildings as long as possible. That's really what we're aiming for. So thank you very much for having me here, and I look forward to any questions. Thank you.
Thank you very much for your presentation. If anybody has any questions, please post them in the live Q&A stream. A question about costs, perhaps. I really appreciated what you said about the materials and the holistic design of buildings, as well as testing. But do you have a sense of how costs might develop?
Yeah, it's a very important question, especially for that very thick CLT panel. And this is something structural engineers are telling us, that if you go up to 7 layers, what we call 7-ply CLT, that's sort of the limit in cost of what people are willing to pay for. And if you go to even thicker 9-ply CLT, then this may be too expensive, right? On the other side, we're still making that calculation in a way that's focused on first cost. Even after decades of pushing this life cycle mindset, that it's not first cost that matters, it's the total cost of ownership that matters. And when you look across the life cycle and across multiple life cycles, if you can actually reuse some of these structural materials, you see a big cost advantage. So it may be that the building gets sold. So maybe the person who pays the first cost isn't the person who gets some of the benefits of reusing that material. But it's certainly something that we hear. And the offsetting benefit, of course, is that these buildings can go up a lot faster. And when we see projects that go over cost, often it's because they take too long. They're over schedule.
I see. So there is cost competitiveness, despite the fact that perhaps in Boston you don't have locally or nearby manufactured CLT. That's good to know. You made a point about the reuse of the CLT floor. How confident are you, your research team, that reuse will actually happen, 50, 70, 100 years into the future, which is a concern, as the previous speaker also mentioned, for conventional materials. But how do you think about that right now?
Yeah, it's such an important point. And there's not much leverage that we in the present have over actions of people in the future. There aren't really clear policy mechanisms to ensure that building materials do get reused. I think about this innovation we have in land conservation. You can put a conservation easement on a piece of land, and you can get some money for that, for basically ensuring that that land is only used for conservation or for farming, for example. And we're playing around with different policies to see, well, what sort of requirements could we put on the owners of these materials that would be contractual, that would basically get passed down to subsequent owners of the building if it gets sold, to ensure that there's at least some attempt to deconstruct materials in the future. I think a lot of times in this field, we say, well, technology in 100 years is going to be so different. How could we guess anything about the future? But I expect in 100 years, we'll still be living in buildings, and we'll still have a construction industry and hopefully a robust deconstruction industry. So the policy aspect is certainly important. The other thing that we're really trying to do is make sure that we have enough structural performance information, that engineers have a standard way of testing whether they can reuse materials. So this already exists very well for steel. So you can do a coupon test, or you can even do a full kind of non-destructive test to see whether a steel member has enough residual strength to use in another building. And so part of the project is to develop the same kind of standards and procedures, to test a CLT to make sure it does have that residual strength, and you can recertify it and put it in a new building.
So those tests do not yet exist long-term for CLT products?
They're in development. right? But we have new kind of species we're trying to use. So any new kind of CLT we develop has to be evaluated and sort of run through the same testing sequence and logic.
And for now, your focus is on the flooring systems, right? Not on other parts of the building for CLT.
Exactly. Yeah, we said the floors are the most important part. The floor is where more than half the carbon emissions are coming from, embodied. And so let's attack that first. And of course, I would love to see all mass timber buildings go up. Let's maximize all the wood we can. But I know that we have big supply constraints. I know that we have hesitation in the construction industry for using mass timber. And at least for the next couple decades, we're going to be building some steel frame buildings. So let's put wood in those. That's been our strategy.
Thank you for that answer. At the beginning of your presentation, you talked about the low carbon materials. Throughout the supply chain, there are lots of claims. There's a lot of innovation around those materials. Could you comment on the scale, though? So if I am a developer or if I'm an engineer, what can I expect to see actually on the market and get on the market right now? How do you feel about the readiness of these materials?
Sure. Yeah. So I don't want to speak out of turn, and I expect several of the other panelists will talk about some of these materials in a more deep way. What I see in concrete is a lot of innovation that can be implemented relatively quickly. So I think low carbon concrete, already we see fly ash used in concrete, and that has penetrated very quickly. It's been used for a long time. But some of these other CO2 injection style concretes or other technologies for low carbon concrete, I can see coming online quickly. The one I'm more worried about is steel. And of course, the articles that I showed early on show that, yeah, we can make zero carbon steel. But in order to do that, we need to electrify all of the mining aspect, and we also need to use reductants that are zero carbon, and mostly that means hydrogen. So the big problem I see is on the hydrogen side. I think I saw a study recently that said, here's how much hydrogen we have, and if we wanted to decarbonize building materials, here's how much hydrogen we need. And it's like a difference of 5,000 or something like that. So we're not going to be able to build 5,000, times our current hydrogen capacity in the next 5 years or something. It takes more time than that to build that kind of infrastructure. So I think even though you hear from the steel industry that they're doing a great job, they have these innovations, as an architect or as an engineer, we won't see that technology penetrate on a global basis for a few decades.
Do you feel different about CLT floors, though? Will we be able to penetrate the market faster?
That's what we're trying to enable, right? We're trying to say, hey, there's all this wood out there that we're not using. Some of it's actually being attacked by insects, or the trees are dying because of climate change, and it's not in their range anymore. So we can harvest that wood and help build up the supply side, and do so in a way where we have structural information and structural testing on these new sources of CLT, new types of wood being used. Then that can help us speed things up.
Wonderful. Thank you very much for your question, for your answers and your presentation. And we're going to transition to our third speaker, who I see is available. Guillaume Habert is a professor of sustainable construction at the Swiss Federal Institute of Technology in Zurich, also known as ETH. where he leads a group of scientists, engineers, and architects whose aim is to ground sustainability in the disciplines of the built environment, which involves interdisciplinary work, drawing on life cycle assessment, urban metabolism, and material science. Welcome, and the screen is yours.
Thank you very much. So I think you see more or less the full screen now.
Yes.
And you should hear me.
Yes.
Yes. So I have a let's say a title that well, this construction industry is already circular, and so where is the problem? And I'm putting this because I think sometimes there is some let's say there is a willingness by somehow the industry of pushing circularity, by the government to push circularity. And I have a question about what are we really talking about when we're talking circularity? Because usually we think materials and we think waste from construction industry. So I will present, let's say, what is happening in Switzerland, which of course is not happening in the rest of the world, but still, I think there is some trends that are that can be generalized. So if you look at the material flow in Switzerland, you realize that's what is the demand, so built environment, and you have the construction and demolition waste, which is these kind of green arrows that are actually kind of circular. If you look at it, you have 8 million tons that is going out. You have already, as a road, 70% that is already recycled in construction and demolition materials. So you know the rules, the 80-20 rules mean that if you're already recycling 70%, the rest to be recycled is probably a lot of effort and a lot of costs to get the last 30%. And if you get the last 30%, if you compare this 8 million ton compared to the 31 million ton that we demand all the time, you will feel 10% of the new demand for the new materials. So my question is like, do we really need to get the last 30% at probably a relatively high cost, at best to fill 10% of the demand, or is there other alternatives? And what? So that's why, like, maybe actually it's already circular, and the question is, it's somewhere else. And for me, the question is somewhere else is when we look at construction and demolition waste in the construction industry, we usually forget what we call excavation materials, because it's just a transfer of earth from one side to the other. So they're not considered as waste. And this one, if you look at the yellow arrows, it's absolutely not recycled. So you have 28 million ton that is excavated. You have a bit that is polluted, that is going in landfill, but you see the unpolluted one, the 18 million, is kind of going to landfill. And then if you compare to the primary demand, it can supply 70% of the current demand. And so if you applied your 2080 rules, we are reusing kind of 2 millions, so 10% kind of of what is taken, of what is excavated. So probably easy to get the other 70%, and this 70% will actually fulfill 70% of the demand. So that's where I think, well, that's what we actually should circularize, and not necessarily the waste of the construction industry, but the excavation materials related with construction activities. I'm saying this, it seems a bit the same, but it's actually not at all the same actors, because excavation material, you excavate when you build the building, so it's at the beginning of the construction phase, while the construction and demolition waste, it's when you demolish the building. So it's not exactly the same strategy to circularize these things. And so, and this, I think there's a great potential to use this excavation material. I just want to show you a few examples, just to say, well, it's actually not new. So using excavation material, basically meaning using earth construction, has been done since quite a long time. I mean, earth construction is basically since humans have left their cave, they built with earth, but in a more, let's say, modern or contemporary construction. We have these beginning of the Industrial Revolution, basically in Lyon, in France, 1870. You have these kind of multi-family houses 6-story high, and you see, because the plaster is not very well maintained, that it's rammed earth here on the wall. So it's kind of a very normal building at the end, but it's actually built with earth. Another building, the same period of time, different country. It's in Germany. Again, kind of a 5-6-story high rammed earth building in 1830. I'm showing you this because it's interesting. Often we say earth is not durable because it can alter it with weathering, etc., etc. It's always, and maybe the analogy is a bit easy, but it's always interesting to think the first concrete building, more or less, that was being built in the, well, at least in Europe, the 1850. That's the 2-story high building of a great engineer, Coignet, architect, an engineer. So at the same moment of time, we were building 6-story high rammed earth houses that are actually still there now, and we were trying to build a 2-story high concrete building that is more or less not here anymore. So of course it means durability maybe is the question of maintenance and not so much of a material. And of course, the question of we might have made quite a few progress in concrete construction between 1850 and now, obviously, because now we are building, let's say, 50 or even more story high building with concrete, and we are still building just 5-story, or even we are very happy if we are building a 2-story high rammed earth houses now. So there's a bit difference between this material, but I still think there is now a kind of renewal of earth construction, and I would like to share with you some nice example. Because the problem, which I didn't tell you this, but the problem with using excavation material, so earth construction, is usually that it's kind of labor intensive, which might make it costly in places where where the labor force is costly. So basically Switzerland and Europe in general. But we have some interesting examples that are trying to bring this, let's say, excavation material in an economically viable way. To make it economically viable, you need to speed up the construction. You need to prefabricate, for instance. So here it's again, like as I said, like a very, very proud to have a 2-story high structural loading with the load on the. I mean, it's the structural rammed earth is the structural materials. So 2-story high rammed earth building, but it's prefabricated, and it's prefabricated on site, which is kind of an interesting way of speeding the construction and keeping the local material. You have other type of construction. So here before was rammed earth, here it's poured earth. So you prefabricate like a concrete wall basically, and then you will assemble so that's a building in Paris. Yes, that is currently built. We also have so that's what I'm showing. What we are doing at ETH, more to work on poured earth, but maybe for on-site applications. So to have a material so this is excavation material with a bit of chemical that I'm happy to discuss with the question. But basically, we try to deflocculate the clay. So you deflocculate the clay, which allows then to have a material that is kind of liquid, or at least fluid enough to look like concrete, let's say. So that you can cast it in a formwork, and ideally you have a deflocculating agent of the clay, and you have a coagulant agent that is removing the effect of the deflocculation. So basically, you put sodium phosphate, for instance, for deflocculating the clay, and you have magnesium oxide that is reacting afterwards on the sodium phosphate and removing this deflocculating effect. And so because you remove the deflocculating effect, you have the same stiff material that you had before. And so you're able to demold and to remove the formwork, and you have like a concrete. This is Nianli Landreau, who was the PhD student that did the work, and he's really happy to have done the work. And now he has developed a startup, mainly, in Switzerland, called Oxar, to promote this kind of on-site poured earth construction. You have other very interesting approach. I'm making a kind of an overview of the rammed earth construction, but just to show that I think there's now a renewal of possibilities, looking, I mean, engineering a bit more the materials. So this is an interesting, it's again like a 1 or 2 story high building. The interesting thing is that it's post-tension. So you have round earth elements that are prefabricated and assembled, piled on top of them each other, and then you have this steel frame. And the steel frame is basically post-tensioning the round earth, and so you have the round earth that is able to accommodate the shear load and still work in compression only, because the steel is taking the shear load. So that's kind of an interesting way of probably a contemporary way of producing round earth and having a possibility of being much higher than just two story high. The other interesting with the post tensioning, it's a project from Erne, which interestingly enough is a timber construction company in Switzerland, who went prefabricated timber element, and they went from round earth. And the round earth, you see so it's round vertically, but then they flip, and you have the post tension, or let's say the tensioning just of the steel that is here, that allows to make the earth working in compression, and then you have the earth that is working for a flooring system. So, and they want to put this in a nice building here. So it means, okay, you can use this excavation material in a very high level and probably high tech engineering way for high rise. I mean, not high rise, but at least let's say multifamily 5-story without any problem, and potentially with the post tension you can maybe have a bit thinner walls and these type of things. You can also have it from flooring. You can have poured earth for if you have a timber slabs, and then the earth on top. So you have many applications, and so I think it's typically feasible to close this loop of excavation material, if we think about excavation material excavation material as earth construction, in that we use, let's say, contemporary way of using these materials. And so if I summarize, it means, okay, the construction and demolition waste, it's already sorted and it goes back in recycled concrete. The excavation material, it could be actually sorted if we could use it as earth construction, I mean, with an earth construction strategy. And so then we have closed the loop. So then we are kind of circular, at least 80%, 90%, and the rest, probably it's enough in terms of cost, feasibility, techniques, and then we still have kind of 10-20% of new materials, and probably we can live with the 10-20% of extra materials. So it means, okay, if it's circular, then why why are we always talking about circularity? And maybe one thing that I would like to show you briefly is that maybe it's because we should not look at the circularity from the material perspective, but we should look at maybe from a cost or an economic or social economic perspective. I just want to share with you 2 case studies, and then I'm hoping for question. So the first case study is a comparison of 2 bridges, one in concrete on the right, one in stone, in a remote region in France, where they have built what it was demolished by a flooding event. The interesting thing is that the two bridges are kind of the same valley. They have exactly the same cost. And from a CO2 perspective, you could say, stone is better, but because you need to put lime between every stone, actually the amount of CO2 is kind of nearly the same. It's 20% better for the stone, but it's not big, basically. So they have more or less the same cost, more or less the same environmental footprint. The big difference is the money. Is, of course, if you look at where the money is going, if you build such a stone building, that's a study we have done where we looked at, how much money is it going for labor, is it going for material, for energy, etc. Then you say, okay, most of the money is going for local labor. Even when I buy material, I actually buy labor of people that have cut the stone. So actually most of the money is, that's what we were saying, 70% of the money is going for salary and for somehow local salaries. So of course the effect, the consequence on the society, if you build such with stone or with concrete, you will have a completely different aspect on, let's say, the circularity of the economy, if I can put it like this. Another example, in a very different context, we look at slum upgrading in Thailand. So you move from a slum upgrading program. It's a great program that has been happening in Bangkok for quite a lot of time. And there again, we looked at the flow of money. We looked at the flow for different slum upgrading possibilities. The first, and again, so you need to look at the initial investment. Then you have in green the material costs, and then in yellow the labor cost. So the first way of improving your settlement when your shelter is, let's say, self-managed. You buy yourself your material, so probably very locally. You hire people very locally also to help you, and then you have an improvement of your settlement. If you don't, so money stay very close to the community. If you don't feel that you're able to build yourself, basically because you have another job than the one in the construction, you will hire a local community contractor. More or less the same amount of money, maybe a little bit more, but you have the local community contractor that again will hire more or less the same people in the community, will buy the material more or less in the same place. It will be more or less the same building, except that you're not doing it, you delegate it to someone. And then you could say, okay, what I will do is a program, and that's what happened in the CODI program. I will do a program where the owner of the building will actually put exactly the same amount of money. The government will bring much more money as a loan that you will later reimburse in 10 years perspective. So you're able to have much more money available. Because you have much more money available, the technology that you're using is actually concrete pillars that you do to avoid your flooding to be flood resistant, which is probably a very good idea, of course. The thing is that doing such technology, you cannot do it with your local community and your local expertise. So you need to hire someone outside that will buy the material outside, that will hire the workers outside, and somehow all the money is then suddenly driven outside the community. You have a better house for sure, but the consequence of the money makes that the money is suddenly driven outside the community. And we even have the case where we realize that in some situation, the general contractor outside the community was hiring informal, so illegal workers coming from the neighboring country that would slip into let's say the unimproved and on the construction site, basically in the slum, in order to rehabilitate the houses of the local community. So at one point, you're reaching the moment where your initial money that you put and that is helped by the government is allowing to have hiring material that is way outside the community, and you even hire illegal workers that will work in the community to improve the settlement. So you have, let's say, from a pure technical perspective, maybe you don't see it, but from a socioeconomic perspective, you have a complete disasters because you're not improving the social quality, basically, except of the single user of the house. So just to put it like this, it means that there is a problem, and we need to look about the money. So maybe to summarize, and maybe to have, we're looking for the question, but what I wanted to say is that, okay, construction and demolition waste, I think they are already circular, at least in some place in the world. In others, we need probably to go towards there, but it is possible to circularize construction and demolition waste through recycling concrete. The problem is that I think is the question of the money, and that this is probably where we should think about how do we, let's say, a circular economy should be also thinking about where is the money going, and not so much from where the material is coming from. How do we map this money, and how do we develop, or how do we choose a technology that is triggering some positive economic loop in the community, compared to another technology that can look very similar, but that is triggering completely opposite, let's say, the development. And of course, there's something that we were discussing before, is like we need to think about the flow of the material. we need to think about the flow of the money. We should not forget that the main target is also the reduction of climate change. And so we should also look at, of course, the embodied carbon and how between two technology, which one has the lowest carbon footprint. Yes, and so to summarize, I think for the use of excavation materials, you have ideas, you have startups, you have plenty of ideas at the moment of people that are pushing for such development, even in economically viable way. I think the money flow is probably the things that is not very mapped somehow. We have the total cost, but we don't know where the money and for whom the money is going. And of course, from the mapping of the carbon footprint, again, I think we have now plenty of tools. I just put a few plenty of tool to map and to make the right decision in terms of low carbon footprint. And with that, I would like to thank you, and I'm looking forward for your questions.
Thank you very much for your presentation. I really appreciate hearing not just about material flows and environmental considerations, but also economic considerations. So important. We have a question in the chat, which I'm going to, the live Q&A, which I'm going to read to you. I have heard of some companies in Europe taking excavated earth from construction and demolition and upgrading, from construction and upgrading it to fertile soil to be used in landscaping. Is this a worthwhile way to reuse excavated earth to reduce environmental impacts compared to reuse it through the rammed earth construction pathway?
So I should check, I think, because I don't know such aspect. It seems at least especially from in a European perspective, I don't necessarily see the interest. I mean, so to make it clear, when we build with earth, we build with the inorganic part of the soil. So typically not the fertile soil, because otherwise you have a very strange smell in your house. So you don't put organic rotting materials in your house. So you build with the inorganic soil. And so the topsoil is usually preserved and moved it another place where you treat it separately. So that you would take the inorganic part and try to fertilize it to make it organic could be interesting if you're lacking the topsoil and that you're lacking type of topsoil. So I can imagine in some place in the world that can be a technique of saying we need to regenerate the topsoil. But in Europe, the topsoil is relatively abundant, so I don't see necessarily the need. But I should check for sure.
But if there was a need, Guillaume, where is your? I mean, that's obviously a complicated question and involves another industry another industry than what you're looking at. But where are you in the environmental assessment, in the LCA of the prefab poured earth product versus the competition, brick, cement masonry unit, poured concrete, CLT?
Yeah. So earth, let's say the vernacular construction of earth, you would have like a zero impact. You could say you're carbon neutral in general. You know, bit of effort, but a few sandwiches and that's all. So it's kind of zero carbon. So of course, compared to maybe pure bio-based construction like massive timber, which you could say store carbon, you're not carbon negative. You're at best zero, basically, which is not so bad. And then of course, if you want to industrialize a little bit to make it faster, cheaper, more efficient, etc., then you add some mechanization, you add some additives for the poured earth. So you will add some. So you would add some. So you will have some additional environmental impact. Yes. So, but then yes, if you compare, to traditional concrete, you're much better. I mean, I would say you're 5 times kind of better. If I need to make rough value.
Yes. Concerns about longevity, durability. I mean, you mentioned at the beginning, right, that buildings that were built as rammed earth buildings are still standing, and perhaps the concrete early concrete buildings are not. But isn't moisture still a problem for your product? How do you see the durability of the material?
Yes. I mean, that's a real question. Of course, my picture was a bit easy and extreme. So Earth construction, if it is, let's say, is not the moisture, it is the water. Like if it is underwater, you have no strength, because the strength is coming from the capillary bridge that are, let's say, with the clay particles that are interacting together. So it's like you need to have if you have water. I mean, you already have tried you sand castle in the beach. It's like if you have water, everything is collapsing. So you need to preserve it from full water, which in normal case don't happen, because you put the earth, so you protect it from the capillary rise from the soil, and then you put a roof. So in a normal case, it doesn't happen. But for sure, if you think durability long term, that's where you will, if you have a damage, that's where you will have problems. And so typically what we see, so more from the old houses, actually, in Lyon, around Lyon, you have quite a few houses like this. It's that you would put on this vernacular house, you would put impermeable cement plaster on the walls, which then let's say hinder the possibility of the water that is going in, that is inside the wall, for whatever reason, because you have a leak, because you have something that is happening. You avoid, you impede the water to go away, and there you have an accumulation of the water at the bottom of the wall. So basically, where you have all the loads, and the house can collapse. So you have, it's not so much that you should remove, you should protect from the water. It's more that you should allow the water to always be able to move away from the wall, because but so that this is clearly an issue in terms of design and in terms of maintenance, but it is not yes, as you said, it's like a long you have example of houses standing for hundreds of years that are still there. It's not it doesn't collapse by itself, basically.
Right. And just sort of following up the thought from the previous presentation about testing, are you performing also testing to be able to show this along with the clear environmental benefits?
Yes, I mean, so you can, I mean, from the environmental benefits, yes, we do some calculation, and yes, it's the question of how much additives you put to improve your performance. That's for sure. In terms of testing from another perspective, which is more the mechanical testing or the liability, where there's a real issue, probably bigger than the durability question of Earth construction, is the variability of the Earth on every single position. So it means, because it is a natural material, it is highly variable. And if you want to have a regular process, certification, etc., you need to have a certain strategy of how do you handle this variability. Either you do testing every 5 meters and you adapt your mix design, or you're back to a certain quarry where you have a regular source. Or yes, but the variability of the material is, I think, the real question, and where we need to have this type of testing strategy.
Okay, and last question, one from the audience. Is there a difference in terms of material use efficiency in the self-construction approach, which you promoted, versus the external contractor approach? Is it relevant in terms of energy use and emissions?
Yeah. I mean, so the case was extreme for many cases. I think we should not. I mean, first, let's say embodied emission of informal housing improvements should not be the question, because the main emissions, they are from the wealthy people in the global north, and it's not the poor person living in an informal settlement in Bangkok, where we should look at the embodied emission of these person. So not from the embodied emission, but from the structural safety, of course. And that's maybe that's really the question, is like, because they put these concrete pillars that allows to be much more flood resistance, because then you're on stitches, you're much more resistant to flooding. But the technology is not available in the local community, so you hire an external contractor. And so I think the question is really the choice of the technology that allows probably the in between. How do you make something that would still be able to be done on site, but provide still an improvement compared to the flood resistance? That would be the ideal situation. But yes, so there's clearly a difference. Yeah.
Great. Thank you very much for your answers and your presentation. And we're going to move on to our fourth presenter. Thank you very much, Corinne Scown, for being here. Dr. Scown is the Deputy Director for Research of the Energy Analysis and Environmental Impacts Division at Lawrence Berkeley National Laboratory of the Department of Energy. Founder of the Life Cycle Economics and Agronomy Division at the Joint Bioenergy Institute, and also head of sustainability at the Energy and Biosciences Institute at UC Berkeley. Dr. Scown's expertise includes life cycle assessment, techno-economic analysis, biofuels and bioproducts, air quality impacts of vehicle electrification, strategies for atmospheric carbon removal, and co-management of energy and water. The screen is yours, Dr. Scown.
All right, thanks. Okay, here we go. We should be all set. Speak up if you can't see my slides, otherwise I'll assume everything is fine. So thanks for having me today. I'm coming to this session as somebody who's really not a building materials expert. That's not historically been my field, but I do a lot of work in life cycle assessment, and I've been dealing with biogenic materials for a long time. And so what I'm going to give you today is kind of what we're starting to do in applying the tools and methods that we've developed in other places to building materials. And I'll kind of bring a perspective that comes from a place of working on bioenergy and now carbon dioxide removal for a while. So there's been kind of renewed interest in biogenic building materials, and that's not just limited to wood, although a lot of that is mass timber. But that can include things like incorporating lignin or hemp or biochar into building materials, et cetera, because people are frankly looking for carbon sinks, places that we can stash carbon away, ideally that's been pulled out of the atmosphere by plants, as part of a portfolio of strategies to, not just decarbonize our economy, which we've been working on for a while, but sort of net remove carbon from the air, because that's sort of the point of desperation that we are at, quite frankly, is that we have to do both of those things now to get on a path where we're avoiding the most catastrophic impacts of climate change. And so that's kind of where this motivation comes from. The project that I've been working on with a few of our other folks here, Arpad and Sabbie, is really focused on sort of sequestering and storing carbon in building materials as a way to not solve all of our problems, but basically buy us some time. So, the idea is like, take as much carbon as you can out of the atmosphere, try to put it in forms that are going to be stable. The rule of thumb is like 100 years, roughly. There's obviously a spectrum of options, from things that we expect will be very, very long-lived, so like geologic CO2 sequestration, to things that are, above ground. They're not going to be as long-lived. Wood building materials being one of those kind of less stable forms. And then perhaps on the far end of the spectrum are things that involve kind of managing agricultural land or managing forests, where you're really, you get temporary storage. It could be re-released fairly easily with sort of missteps. And the way we frame this is that you're sort of renting that. And I think Matt alluded to that earlier, that it takes continued investment to keep that carbon from going back into the atmosphere. But today I'm going to talk specifically about building materials, and I'll kind of touch on pavements and stuff at the end. So as I mentioned, these products are not a panacea. This is a nice paper from Nature Sustainability that was published a few years ago. But the idea is that we can start to use our cities as carbon sinks as part of this portfolio of options for removing carbon from the atmosphere. So like, what materials specifically are we talking about? There's a lot of options. I mean, we talk mostly about wood, but bamboo comes up, as you saw in the previous slide. And then there are other types of biomass, kind of agricultural residues, dedicated farmed biomass that you can either use as is or use some component of it after processing to incorporate it into building materials. So one example is hemp. This is something that we've been talking with some of our agronomist friends with quite a bit. It's of interest in the LCA project that I mentioned that's funded by ARPA-E. And there are a lot of farmers growing hemp and sort of other products along those lines. And sometimes you're just trying to extract a very small part of the plant. So like there's a whole industry that's cropped up to extract like cannabinoids out of these things, and you have a lot of fiber left over. And the market for that stuff is immature. It is a burgeoning market. They are trying to find value-added uses for all of this fiber. And so that's where we've started to look at options like, quote unquote, hempcrete, incorporating hemp into concrete. The same goes for other byproducts of bioprocessing. So ash, depending on the temperature that you are burning biomass at, can offer pozzolanic materials for concrete. And then lignin and biochar are two byproducts from some fairly well-studied processes for converting biomass to fuels, chemicals, etc. So typical biomass comprised of lignin, cellulose, hemicellulose, and then some other components that can be kind of starches, acids, etc. And that lignin piece has historically been very, very difficult to turn into anything of value. People from the pulp and paper mills will certainly tell you that like this sort of black liquor or craft lignin has been challenging to valorize. And so there's some notion that maybe you could incorporate that into concrete and get value out of it rather than just burning it, which is the alternative. Similarly, biochar is something that can either be your primary product, or it can be a byproduct if you're pyrolyzing biomass and you're trying to make either like a liquid or primarily a gaseous product. If you're doing gasification, you'll usually get some amount of biochar, and that can also be incorporated into bioproducts. In fact, if you go and look at what's going on in the carbon dioxide removal or CDR markets right now, the vast majority of the transactions are all related to biochar. So you can go to cdr.fyi and see just a long list of people making and selling biochar as sort of cheap carbon removal to the degree that that works. So as I mentioned, the composition of these materials, and we usually refer to them as feedstocks, varies quite a bit. So cellulose, usually 30 to 40%. Hemicellulose, maybe 20 to 30%, although that can vary a lot depending on the species. And then you've got all of this other stuff. Ash, that would be the fraction that you could incorporate into cement, proteins, etc. And so not only does this vary by the plant that you're looking at, it also varies by where it was grown and under what conditions. So like a plant that was subjected to drought stress might accumulate more lignin than a plant that wasn't. It'll be impacted by the time of harvest and the maturity of the plant. And your results will also vary depending on what analytical method you are using to try and figure out what the composition is. So unfortunately, the easy way to do it, near IR, also does not necessarily give you as accurate a picture of what's going on with that plant than using the kind of labor-intensive wet chemistry methods. And so that's just a constant challenge when we're trying to do like high throughput screening of plants for different applications, that, you know, the compositional data is really not high throughput to generate. And any of the high throughput methods give you like worse data. So that's just something that hinders our ability to develop predictive models. And it's certainly something that there's ongoing work on to try and figure out how to better screen these things in any kind of efficient way that doesn't just require a lot of people in the lab. But biogenic materials, you know, for all their challenges, play a central role in any carbon removal future that we can imagine. So these are some preliminary results from a report that is forthcoming in early December, so very soon. And this report is called Roads to Removal. It was supported by the U.S. Department of Energy, kind of several parts of DOE, and some philanthropic funding as well. And we looked at a bunch of different strategies, including forest management and biomass with carbon removal and storage, or what we refer to as BIKERS as an acronym. And so you can see that basically the cheapest carbon removal that you can get is all around forest management. That's the green piece here. And so you can see shelter wood harvesting. So harvesting some of these large trees to kind of make room for saplings to grow, forest thinning, has a negative cost. It pays to do that. Additionally, you can do some forest restoration and use that wood for building materials, and that has a very, very low cost. Basically, everything else costs quite a bit more than the forest management pieces. The other thing to know about forest management and its kind of intersection with the market for building materials and the market for carbon removal is that it's something you can do now. You don't have to wait to build a bunch of facilities and establish markets for products that there aren't necessarily markets for now. So at least from the perspective of like the carbon removal community, we see forest management as being one of those things that you should do first. It is like the low-hanging fruit, and it has all kinds of interesting co-benefits beyond just getting carbon out of the air, putting it in wood products, or in some cases, you know, you may be doing prescribed burning, but we want to get as much of that into stable form as possible, and ideally have it be something that you can make some money off of. And so that's what this shows, that forests in the long run have less of a role to play in the annual carbon removal that we think is possible, but that forest management and the resulting forest products have the biggest role to play, one of the biggest roles in the near term. And the cumulative carbon removal that you can achieve between now and 2050 is really quite high for forests. So, you know, that's why I think buildings are like, one could argue that they are a smaller carbon sink than what we ultimately need when we start doing large scale, like geologic storage of CO2, which I know is controversial to many. But forests for between now and 2050 are going to play a really, really big role. And that means building materials are going to play a big role. So the other thing to note, and these are results that are in the Roads to Removal report. This is led by Sarah Kubing from Yale and her team. So full credit to them for this analysis, is that the availability of these building materials, the availability of wood, is going to depend a lot on a very uncertain future that is impacted by climate change and also impacted by our choices around sort of how we manage forests. So they split the strategies between exploitation focused and regeneration focused. And then of course there's the kind of no disturbance, like no extreme events, nothing happening with weather, with pathogens, etc., and you can accumulate quite a bit of carbon. That goes down a lot if there are extreme weather events, or you have the combination of extreme weather events, so like drought, for example, major storms, and pests and diseases. In all of these cases, that also impacts the baseline. And so it doesn't mean that you shouldn't change the way we manage forests and take some of those trees for wood products. It just means that, like, you know, it's going to impact how much carbon you're ultimately able to remove and put into a stable form. But relative to the baseline, no matter what, you should be pursuing these options because it does make a difference. Focus on what we can control, right? So, you know, assessing the impacts of these wood materials is really complex, not only because it depends on how you're harvesting them, where you're harvesting them, and what you're harvesting, but also, you know, what are they getting used for? What does the market look like for these things? And so we have to bridge this gap between forest management modeling and the production of usable building materials. And I'm certainly not the first to make this observation, and there are plenty of really smart folks working on this. We are hoping to bring our kind of unique perspective plus LCA expertise to try and kind of add to this body of literature and give people a framework for kind of modeling the impacts of these biogenic building materials. And we're starting with wood because that makes a lot of sense. The other thing to take into account in these life cycle assessments is, as I mentioned, kind of co-benefits that don't have anything to do with greenhouse gas emissions. Our focus in this project is primarily on carbon to start, and just understanding the carbon flows and understanding how much carbon we can remove from the atmosphere and store, at least temporarily, in building materials. However, these are some nice results published a couple of years ago in PNAS looking at the air quality impacts associated with wildfires in the US. And it contributes a really like shocking fraction of fine particulate matter concentrations in the US. And so what you can do down the line, hopefully, is incorporate some range in terms of the net human health effects of implementing forest management strategies that yield a larger portion of wood building materials. And you can incorporate that into sort of predicted reductions in wildfire risk and predicted reductions in PM concentrations. I think there's like several logical jumps there. So this is definitely a tall order, but it's something worth getting our head around, because it means that some of those strategies that are already low cost from a carbon removal standpoint probably sort of flip from being very low cost to being negative when you start to incorporate some of these other externalities, these positive externalities. So what are we doing in the near term? This is like an incredibly complicated problem. You have to start somewhere. And so where we're starting is these kind of decision tree algorithms. And we actually started doing decision tree algorithms in my group a little while ago to tackle an entirely different problem. We were trying to figure out how to incorporate what's called downstream processing, or DSP, into our techno-economic models. And a lot of times we would be taking results from the lab. Nobody had done the DSP yet. They didn't really know the best way to recover and purify their product. And so we had to kind of deal with some uncertainty that, like, you hadn't tried this stuff, you didn't really know what would work. Maybe you had some expert judgment on like what you would try first, and if that failed, what you would try second, and what you would try third, etc. And through that process, we developed this kind of decision tree algorithm for saying, okay, you know, tell us a little bit about your product. And it's okay if you don't know. The I don't know is usually an option. And you can kind of go down and you drill down into more and more detail until you've got all the information you can possibly get. And then you basically come up with recommendations for, in the case of the DSP, we were looking at like, what does this process configuration look like? And then translating that into costs and emissions from there. In the case of building materials, we're trying to kind of walk people through, like, what do you know about your biogenic building material? So how is the forest managed? Is it a land cultivated species? Like, are you applying herbicide basically? Are you like sort of farming trees? Yes or no? Is it a softwood or hardwood? What kind of logging treatment are you doing? Is this clear cut or shelter wood removal, selective cut? How far is it transported? Where is your mill? All the way down, you kind of what product are you making? And so while we're still building this out, I think this is a really helpful way to start tackling these problems in a transparent way, while acknowledging that I don't know is often going to be the answer when we ask these questions. And the more you learn about kind of standard practices in different countries and different regions, the more we can build in better answers when you don't know, right? We want to have the best possible defaults when you may not have the best information about the material that you're using. And so you can expand this, you can sort of tackle greenhouse gas emissions first, and that's what we're doing, but you can expand this to cover all kinds of relevant metrics. I mean, you can do cost, air pollutants, human health, et cetera. And so that's kind of ultimately the vision with this, is to create a transparent way to get the best estimates that we can, acknowledging that we don't have all the information that we would like to have. And then finally, what's counterfactual product? Like, what are you replacing? And so sample results, at the end, you get something that looks like very similar to a typical LCA. And, this is all still kind of early results, but that's what it might look like. In terms of herbaceous crops, we're kind of tackling this separately, and they're sort of actively managed, dedicated fields in some cases. And so you can use agroecosystem modeling or biogeochemical modeling to tackle these questions about like how much soil organic carbon is getting sequestered, how much nitrous oxide is emitted based on expected fertilizer application rates, et cetera. And so these are some results that are coming out in PNAS later this week, I think. And we'll be kind of incorporating that for herbaceous products, things like hemp, other ag residues, et cetera. And finally, I just want to touch on this question of incorporating bio-based materials into asphalt and concrete. This is something that we haven't yet tackled as much in our project. But bio-oil was actually a really interesting situation when we were doing the analysis for the roadster removal report. The kind of optimization model really thought that making a lot of bio-oil and putting it in asphalt would be like a great carbon removal strategy. And we had to place some constraints to keep it from doing that. But it does raise this question of like, how real is this? Like, is that carbon stable? Is this something that we should be pursuing? There probably needs to be more research on like what that does to the performance and how much you can realistically blend. But that's very much something that would be interesting to keep looking at. And, and again, incorporating lignin, incorporating ash into concrete, we have to understand what that does to the performance. And that's something that Sabbie Miller, my fellow panelist, is much better suited to answer than I am. So finally, people might be saying, okay, all these like wood materials and stuff, but like, what about the polymers in buildings? We use polyurethane, we use PVC, we use all kinds of stuff. Like, is that a good strategy for taking biogenic carbon and storing it in buildings that might sit around for several decades? Basically, I think the answer to that is like, nah, I wouldn't prioritize that. The reality is that like most of the polymers that go into building and construction are not ones that we are typically targeting as bio-based products. And they also have a relatively low carbon content. So PVC is like 38%. Other polymers are just a much better fit for that. They're 70 to 90% carbon. And, ultimately we want to promote, I think, circularity over trying to treat these as sort of carbon sinks and then landfill that material. So looking ahead, we're going to keep building out this decision tree approach. I'd be happy to take some feedback on that. And with that, I will wrap up and just acknowledge some of my wonderful collaborators and some of our funders. And I'd be happy to take questions.
Thank you very much for your presentation. So all four presenters today thus far have emphasized the importance of timing, and you certainly did that too. So there are certain things we can and should be doing in the short term. Just to sort of go back to that idea, would you kindly summarize what are the actions in the sort of biogenic material space that we should be doing right now? You touched upon several material classes. So in short, what are your recommendations?
Yeah, that's a great question. I think pursuing mass timber, if it is pursued in parallel with forest management approaches that will help us kind of reduce wildfire risks, accumulate carbon in a sustainable way in our forests, like that seems to me like, as I mentioned, the lowest hanging fruit. And I'm perfectly happy with just starting there. I understand that the construction industry is risk averse, understandably so, right? And so there may be some other strategies that look like they have greater potential. I mean, I've seen all kinds of crazy stuff show up in research papers that would increase the potential for buildings to be carbon sinks by, replacing concrete with some crazy new thing. But at the end of the day, I know from experience how difficult it can be to get anybody on board with using a new material that they're not familiar with. And the timeline for testing that stuff and proving that it works can be so long and so arduous, and a lot of those things will fail. And there's all these points along the process at which somebody can just veto your material, especially in the construction industry, right? So when we have stuff that works, I think we put as many resources as we can toward doing that. So that's why we're focusing first on wood. All right. It's kind of our top priority is figuring out where you should scale this up, how much are there particular forest management strategies and species that are most promising, and then building tools to enable those so that people understand what is the net greenhouse gas balance, what are any sort of interesting co-benefits that we can capture with a life cycle assessment framework.
Thank you. Would your tools be able to capture all kinds of biogenic materials, all kinds of biomass, or is there sort of a hierarchy of some materials being better captured, maybe higher certainty in data versus others that are less certain?
Oh man, I mean, there's uncertainty all around, right? That's the whole idea with this kind of decision tree algorithm is that you are operating in a place of great uncertainty. I think we have a lot more simulated data to go on for agricultural products. So things like hemp, things like agricultural residues. I don't want to say false precision, but we've got these very specific numbers of here's how much carbon will go in the soil and here's what your yield will be and stuff. I have heard people say there's a big gap between what those models like Descent predict and what the experience actually is. So I think from a modeling standpoint, it's probably even easier to do those kinds of grasses, other agricultural products than it is to do the forest products. But I don't know that the precision we can achieve necessarily reflects less uncertainty. We kind of have to see how that plays out. And a lot of it will be impacted by what goes on with the climate. So there's this feedback loop, and we can't say with certainty where that's going to land.
You certainly made very good points about the variability of the materials in this space, right? So kind of to wrap up the questions here, what is your overall sense of the confidence that we can have in the biogenic data and decisions nowadays? So, everybody's is hanging their hat on biogenic materials as being the savior for a lot of things. And so what is your overall confidence? How good is our decision-making right now?
Well, I think we have enough information that I'm not as skeptical as some people might be about all biomass, right? There are some people who think you just can't trust it. And there's a reason why on the CDR market, all of these bio-based solutions tend to sell for less money than other stuff. People are willing to pay way more, probably absurdly more for a ton of CO2 removal via DAC, direct air capture, than they are for a bio-based solution, which is interesting. I mean, it's just all DAC just costs more, so it wouldn't even exist if they weren't willing to pay more. But I'm actually quite hopeful, because there is this burgeoning field of measurement, reporting, and verification, or monitoring. They have different M's depending on who you ask, but MRV. And there's a demand for it from like the regulatory side for implementing agricultural carbon management, or sort of climate smart farming practices. The government wants to pay for this, but they want to be sure they're getting what they pay for. There's also a demand for it from even private carbon markets. And so there's a real push to develop lower cost strategies and figure out like what's the cheapest way that we can get the most information from these fields. And you can supplement that with satellite data. There's ways that we can get more measured data one way or another to make sure that when we sort of count on a certain amount of carbon removal, we count on nitrogen fluxes being a particular way, that like that's actually what's happening on the ground. So, you know, I think we're headed in the right direction. And I think it has to play a big role. If it doesn't, like, we're going to end, this is all going to be way, way more expensive. So we've got to figure out a way to make it work and give ourselves the confidence that it is working.
Great. Thank you very much for your answers as well as your presentation. And right on time, we are going to transition into our plenary talk, and keynote speaker, Professor Sabbie Miller from the University of California at Davis in the Department of Civil and Environmental Engineering. Professor Miller's research focuses on lowering the environmental impacts of the built environment, specifically methods to quantify, assess, and mitigate the climate and health burdens from materials, while also improving material performance. So your presentation is going to cap the Infrastructure and Sustainability Day as well as the conference, and we're looking forward to it.
No pressure. That's good. Thank you so much for the invitation. I will share my screen right now. And I'm going to assume that we're sharing properly unless I'm told otherwise. Great. Okay. So thank you again for this invitation to present. I'm really thrilled to talk about the current perspectives and other environmental impacts that we can attribute to building materials. So I'm sure everyone on this call is well aware, we have some really pressing measures that we need to reach really quickly in terms of how we could start to mitigate our greenhouse gas emissions and ensure that we limit continued environmental damage associated with the greenhouse gas emissions that we're producing, as well as other impacts that we're currently producing in our production pathways. So right now we have several unsustainable patterns that we are following as a society. One of them, sadly, is tied to materials production. So this is a pie chart of greenhouse gas emissions. It's just a snapshot of 2016. And in 2016, approximately 30% of our greenhouse gas emissions could be tied to materials production. So it's not exclusively the chemical reactions in the materials or the energy for the materials, but also their supply chains associated with them. But an entire almost third of our greenhouse gas emissions just to produce the materials that we consume. And a lot of those materials end up in the built environment, which is why there's such an emphasis on, well, can we turn those into a carbon sink? So this chart is just showing a handful of the materials that we like to use in the built environment. You'll notice that wood is not on this chart. It's also one of our large consumers, although nowhere nearly as high as concrete. And just to give you a sense of approximately how much of these materials we made, again, this is kind of a snapshot in time. There's approximately 0.06 gigatons of aluminum made annually, around 0.4 gigatons of plastic. So as Corinne just mentioned, this isn't going to be our biggest sink because it's not a huge amount that we're producing, a little bit under 2 gigatons of steel, approximately 2 gigatons of asphalt pavement, again, tying into that last presentation of, ooh, maybe this is a location where we could start to place some of our materials that we want to turn into a carbon sink. A fair amount of bricks are produced annually, although the data are not perfect there, and around 30 gigatons of concrete. Now, of course, this does pale in comparison to some of our other consumption patterns. Specifically, we like to use a lot of water. So in terms of our demands as a society, we have large consumption patterns elsewhere as well. But to have this much of our solid mass being something that we're synthesizing annually, well, how can we start to engineer that better to both mitigate those huge emissions and then, of course, potentially turn it into a net benefit instead of a net harm to the environment? And of course, we have to do this in a balance of, well, what do we actually need? And keeping in mind that we've had a pretty linear increase in population, this is one of our primary drivers. So if you look in kind of 22-year chunks, we went from 2.7 billion people on the planet all the way up to exceeding 8 billion people on the planet in a very, very short time horizon. And in that same time horizon, we had a massive escalation in gross domestic products, basically huge escalation in wealth and affluence at the same time. So as I'm sure most folks on the call are well aware, we can oftentimes see the impacts associated with society are tied to factors such as the population growth, such as affluence growth. And oftentimes we're relying on technology breakthroughs in order to mitigate impacts if we have growing population and growing affluence as we currently do. And specifically with our built environment, that's where the vast majority of our materials are going. So this is approximately the mass of materials that were produced and used from 1900 up to 2015. And you could see that, yeah, we needed a lot of food and feed for our animals as well. We also consumed a bunch of energy in that time horizon. However, if you sum up the food, feed, energy, and other materials that we were consuming, it about equals the amount that we were sticking into the built environment. So how do we start to re-engineer our built environment to have more benefit? And again, this ties back really heavily to the fact that we are having continued escalation in consumption, and the built environment is where we use our materials for the longest period of time relative to our other consumption patterns. So here we're showing world production in terms of kilograms of materials consumed per capita, where wood consumption over this short time horizon stayed relatively consistent per capita, but keep in mind the population skyrocketed. Our steel actually increased per capita, but again, keep in mind the population went up, so this went up even higher in terms of total consumption. Cement consumption per capita went up significantly faster than our other materials. And then on top of that, this is just per capita, so even more consumption. And if I had tried to plot concrete on this chart, which is a composite material made out of cement, water, and aggregates, well, concrete production is about 7 times higher than cement production because cement is just one constituent we put into the concrete. We would not have seen our steel and wood lines per capita. They would have just been sitting right at the bottom because the concrete would have made this scale astronomically high. So what we end up seeing is, okay, not only do we have growing population, not only do we have growing affluence, but per person, we're driving up the amount of demand that we have. And then pairing that with the fact that we hold on to our materials in the built environment for significantly longer than all of our other applications, we're seeing an accumulation of materials in the built environment. So this is a chart from a study that was published in the Proceedings of the National Academy of Sciences showing global in-use material stocks. So basically the materials that we're currently using. So it includes the materials we're producing each year, as well as all the materials we're still using from prior years. And as you can imagine, well, we like to use our roadways for a long period of time. We like to use our buildings for a long period of time. We're going to hold on to those materials for a long period of time. And as we could see, concrete, asphalt, bricks, aggregates that we're using as things like road bases, those are making up the vast majority of the materials that are currently in use. So not only the materials that we produce a heck of a lot of each year, but also the ones that we are using for so long that it's such a large mass of materials that we have in the environment that we've synthesized. So what this means in terms of environmental impacts is a variety of things. First of all, we like building materials. We like to have buildings. We like to have roadways. We like to have sewer systems. So we need those materials for things like structures and services. And of course, in order to make materials, well, we have to consume a certain number of resources, right? They don't just suddenly appear out of thin air, and we need a certain amount of energy to process those resources. Also, we need a certain amount of energy for our structures and services. So, for example, my computer is on right now and plugged into the wall. I'm using electricity. So we also need that energy for the structures. And of course, depending on the materials we pick, it could actually influence the structural thermal demand and other aspects of the structure's energy consumption. And of course, we actually need the structures and services for our energy supply, right? We actually need materials to facilitate access to our energy resources. So there's a little bit of a circularity showing up right here. But of course, that's not where it stops. In reality, we don't have any perfectly efficient ways to produce our building materials, so there's going to be some waste in the processes that we use. And then on top of that, we have greenhouse gas emissions associated with things like just simple chemical conversion from producing those materials, as well as the energy resources that we use for those materials. And then on top of that, we also produce air pollutants from the energy resources themselves, because we're still kind of fans of fossil fuels, and from the building materials themselves. So this could include things like particulate matter from quarrying activities. That could lead to localized air pollutants. And of course, localized air pollutants then could lead to health impacts. And actually, greenhouse gas emissions can lead to climate change, which can lead to health impacts. And of course, we know that there's an energy-water nexus. So our water demand relies on a certain amount of energy, and our energy relies on a certain amount of water. And we also use water for the processes to make our building materials, for things like dust suppression, as well as chemical reactions that are necessary. And then on top of that, we also have the potential for water contamination from like mining activities for our building materials. The list goes on. Basically, any change that we make for these materials, if we're trying to decarbonize our emissions, or if we're trying to tackle some other challenge like air pollutants, it could have a more networked effect and include things like Corinne mentioned, changing the functionality of the services and structures that we've become so reliant on. Now, tying back to greenhouse gas emissions, since that's what we've been chatting about a fair bit today, well, okay, we know that about 30% of the greenhouse gas emissions in 2016 could have been tied to our production of materials, but which materials exactly? Well, a fair bit was tied to iron and steel, as well as cement production. And keep in mind, cement is just one constituent in our concrete. For both of these, not only do we consume a lot of cement annually, about 4 gigatons, and a lot of steel, again, about 2 gigatons. But for both of these materials, we also have chemical-derived emissions, basically the chemical conversion processes that are used in our blast furnaces from our iron ore, the iron oxides. That reduction can lead to carbon dioxide emissions. And in our cement production, the limestone decarbonation, that's a precursor to the final cement, that can lead to some carbon dioxide emissions. And then on top of that, we have energy inputs for all of these types of materials. So how do we start to decarbonize, as well as ideally lead to a carbon uptake mechanism? And then, of course, how do we pay attention to those other impacts as well? So just using concrete as an example, because we consume so much of it, well, about 3% of our energy demand every year goes into the production of concrete. We also end up seeing that emission of dust can lead to things like about 5% of our PM2.5, anthropogenic PM2.5, so not including the forest fires that Corinne just mentioned. We also end up seeing that the fuel resources, as well as if there are any sulfates present in the mineral deposits used, can actually contribute to about 5% of our global SOx emissions every year, just from producing our cement and concrete, and around 8% of our NOx emissions. So if we go in with a strategy that's targeted at decarbonizing or targeted at creating a carbon uptake mechanism, well, we got to make sure that we're not going to increase a lot of our other burdens that are also going on for the production of this material. And that also ties into resource consumption patterns. So we end up seeing, if we have to produce things like 30 gigatons of concrete, well, we need some resources for that. And that includes things like sand, aggregates that are used, so larger crushed rocks that are used in the material, water consumption, both for use in the material directly, as well as all of these processes that get leveraged. And then, of course, energy consumption. And we've actually seen that less than ideal management of those resources can lead to localized scarcity. So perhaps we do have plenty of sand on the planet, but is that sand the correct characteristics that we need for concrete? Is it in the correct location? Are we managing those resources properly? Or are we causing a localized depletion or other localized social instabilities associated with that high level of consumption tied to the materials? And if we want to make a change, how do we target those other issues that could come up at the same time? And one of the best ways to do this is to, as all the other speakers have mentioned, design throughout the entire life cycle. So what resources can we leverage? If we start to switch the resources that we use, can we actually have co-benefits? Can we actually minimize the other burdens that we would tie to the built environment? What manufacturing alterations can we start to leverage? Increased efficiency is fantastic. That's going to lower our energy demand. That's going to lower the emissions associated with energy resources. But how broadly can we apply more efficient technologies? Are there other ways that we could start decarbonizing at the manufacturing stage? How applicable would things like carbon capture and storage actually be for different types of technologies that are getting utilized? For transportation and assembly, how can we improve material efficiency, for example, at the construction stage? Can we start to have less construction waste for some of our applications? How can we start to leverage resources where we wouldn't have to transport the goods very far, potentially increasing transportation-related emissions from increasing that distance, but also displacing some of our impacts? So it kind of pairs with NIMBYism, right? I don't want that construction facility in my backyard, so I'll just move that facility to another location, drive up the greenhouse gas emissions from schlepping the material back to my particular location, and also displacing any localized air pollutant production to some other location where a different population has to get exposed to it. And then, of course, how can we start to improve use of these materials? How can we elongate the service life if the material is still functioning so that we can maintain any carbon that's stored in it and potentially offset the demand for new material production? If we do have to dispose of this material, what's the best way to dispose of it? Should we try to lock in whatever carbon's there? Should we try to recover some energy? And can we actually recover the raw material itself to offset our demand for resources? And of course, as was mentioned by Corinne, we have to pair this with what the material must do. This is a cartoon sent to me by a friend where basically somebody's talking to a scientist and saying, we've made your environmental report greener and now uses 50% less paper, but that is not going to perform properly as a report. Try reading something where half the paper has been cut out. And so, of course, as we start to pair this with the built environment, if these are the materials that we use for a long period of time, these are the materials that we need to have be durable for a long period of time, maintain their functionality for a long period of time. So how do we integrate that with our quantification of environmental impacts in order to make the most sustainable solutions? And of course, material efficiency plays a really strong role in this. This is kind of a reboot of a material use hierarchy where we're focusing predominantly in on building materials, where things like less construction or more efficient cross sections of members can start to drive a reduction in the actual amount of materials that we need to consume. If we do need to consume those materials, how can we start to better reuse them? Can we start to use standardized component connections, prefabricated panels, as Professor Eckelman mentioned, all of these ways to start to leverage that material over and over again? If we can't continue to leverage the material because maybe it's lost some of its performance, can we start to recycle the resources? So again, we could start to offset resource consumption, and this can include things like using those resources as new material generation. Can we recover anything from these materials if we can't recycle them? Maybe we should be trying to leverage them for energy resources if they have a certain calorific value. Or are we actually better off landfilling them and storing that material in the soil for a long period of time. And of course, pairing that back with where are we consuming those materials? Well, keep in mind that by weight, we are using a significant amount of building materials currently. And then, of course, keeping in mind how producing those materials ties to greenhouse gas emissions. Well, just as an example, cement, it's pretty close to a 1-to-1 ratio for the amount of greenhouse gas emissions per kilogram of cement. So approximately 1 kilogram of carbon dioxide equivalents per kilogram of cement produced. It's a wee bit lower, closer to like the 0.8 region. In terms of our aggregates, which are used in concrete, that's a huge mass of materials, but it's mostly just quarried and crushed rocks, which means not too high in terms of the greenhouse gas emissions per kilogram of aggregates. And in fact, the huge amount of emissions tied to aggregates is only a function of the huge amount of aggregate production, right? So it's much smaller than the production of cement in terms of greenhouse gas emissions. In terms of wood, well, yes, there's definitely emissions associated with things like sawmilling activities, transportation, but there's also uptake associated with wood. So how do we start to balance all of these parameters along with decarbonization efforts and tie them to these goals of carbon uptake? Well, if we need all of these materials for long periods of time, we could start to re-engineer them ideally as a carbon sink where, for example, our aggregates are a huge mass of materials. They're already relatively low emissions in terms of production. Maybe we can come up with a pathway that leads them to be a substantial carbon sink. Or if that's too difficult, because that would require potentially a lot of resources to create that carbon sink, maybe we'd be better off trying to re-engineer something where we already know strong pathways to create a carbon uptake mechanism, because maybe that is going to be a lower hanging fruit. So for example, the plastics and woods that have been mentioned already today. And of course, keeping in mind how much renewable versus non-renewable resources do we actually demand. This is just a snapshot of the United States for a 100-year time horizon. And you could see that we've had a pretty strong pivot towards the utilization of non-renewable materials in terms of the mass of consumption that we've been demanding. This is in large part actually tied back to those aggregates that we use in concrete. We have a lot of concrete in this country for our roadways, our building foundations, our sewer systems, et cetera. And we end up having a large weight fraction of concrete being present. So even though we're still consuming renewable materials, we actually have a large mass that's from non-renewable resources. So how can we start to pivot that towards renewable? And then, of course, keeping in mind that our renewable resources, as we currently consume them, aren't directly going into the built environment consistently. So yes, we absolutely do produce lumber. And yes, that has a relatively long in-use period compared to some of our other biogenic materials. But we also produce a fair bit of paper and board. In fact, that's one of our bigger sources of where we send our wood-based materials. We also use wood-based materials as an energy resource. And for energy and these shorter-term products, we don't necessarily hold on to the carbon as long as we would for a building material application. And that could actually lead to, as have been discussed, these dynamic fluxes where maybe it took decades to absorb the carbon dioxide, but we're releasing it at a slightly different time horizon. And that brings us to how we could start to re-engineer the materials that we're already big fans of. So bioplastics were already touched on in the last presentation. Just to kind of give you a couple of different areas that these have been explored. Well, there's TPS as a bioplastic that has been explored using things like reclaimed potato starch, corn sources. We've seen a lot of biosynthesized plastics that already have the same molecular structure as our conventional plastics. So instead of a petroleum resource for the carbon, it's a bioresource for the carbon, but it's the same molecule structure. So that includes things like bio-PTT, biopolyethylene, bio-high density polyethylene, polyethylene terephthalate. And we have a fair number of plastics that are synthesized that are from bioresources, but don't necessarily have an analog in the current petroleum-based resource plastics. So that includes things like polylactic acid and polyhydroxybutyrate, where we are able to synthesize these plastics, but they don't necessarily map directly onto a conventional plastic. And of course, there's many different carbon resources that we could be using for each of these types of plastics. These include things, as I mentioned, like the potato starch, corn, wheat, sugarcane. We actually see the potential for landfill biogas, somewhat uniquely for the polyhydroxybutyrate. There's other pathways for it too, but interestingly enough, polyhydroxybutyrate can be synthesized with microbes that can be methotropic. So you could actually feed them the methane from landfill biogas directly. We also see different types of oils getting used. So rapeseed oil, used cooking oil, to try to synthesize each of these different types of bioplastics. But as was discussed, how do we make sure that these can actually map directly onto something that has a different performance? So let's zoom in on polyhydroxybutyrate. Well, again, that was one of the ones that could get synthesized in microbes. And this is actually an image of bacteria that are collecting polyhydroxybutyrate in the cell structure. So that's actually the polymer right in there. If we were to combine it with a natural fiber, we actually could start to make composite materials. And in reality, those composite materials can behave kind of like wood, which means that we could be using a waste product from the lumber industry, combining with a plastic that can get synthesized in a matter of hours. Usually we're talking about in the 80 hours time horizon for these bacteria to synthesize the plastic and create a wood product. That then could get used in similar structural applications to what we're already familiar with. It could be sent to a landfill where, yep, it would anaerobically biodegrade. That could then lead to both carbon dioxide emissions and methane emissions. But wait a minute, the biomass that gets used in the plant matter, that uptakes carbon dioxide emissions. And we just said that those bacteria, they could be fed by methane. So we actually have a chance of creating closed carbon cycles. This is not exclusive. There are many different ways that we could create closed carbon cycles, but this is just one example with a bio-based composite. And this is just a snapshot of some of the bio-based composites that we've been engineering in our group, as well as some of the mechanical testing that we've been performing on them, because again, we need to make sure we get the same performance if we want to replace our conventional materials. Here's just a quick image of scanning electron microscopy where we're starting to see how we can improve interfaces between our fibers and our polymer matrix if we want to drive up an increase in mechanical properties. Where you see here, no treatment whatsoever leads to a pretty big gap between the fiber and the matrix. But if we start to apply a coating on the fiber, we could get a better bond. Or if we start to graft the polymer, we could get a better bond between the polymer and the fiber. And why that's important is that we can start to engineer even better material performance than what we're used to. So here we're looking at a conventional polymer decking. So you might have seen these, Trex is a really common brand of these. Here we're looking at a modulus of elasticity. Here we're looking at a strength of a material. And you could see using different types of natural fibers in this polyhydroxybutyrate matrix, we're able to synthesize composites that have significantly higher elastic stiffness and significantly higher ultimate strength. We are also able to then pair that with our conventional design to say, wait, can we get a little bit more efficient then in terms of the amount of material we need? If we have great strength properties, maybe we don't need to have as large of a cross section, or maybe we won't have to replace this material as often. And so you could start to look at this, pairing it with structural design and say, well, if we have deflection controlled members, and if we exceed that deflection, maybe we need either more material or we need to replace it. How do we pair that with the longevity of these materials? So here I'm showing that conventional deck as well as those polymer-based composites and their typical lifespan before they reach those deflection limits. We could then couple that with life cycle assessment, where here we have our cumulative impact. So impact at time 0, produce a material, impact at time 1, replace that material so that you don't exceed the deflection limit. That means we've driven up our impact. And compare it across a bunch of different materials, where we could actually see that if we're able to engineer a material that, even if it has slightly higher impact on day 1, if we don't have to replace it, we might be able to hold on to that carbon for longer and not have the burdens associated with additional production. Now, of course, we could expand that kind of mentality to some of our other materials. Let's focus in on concrete for a second, because we consume so much of it. And keeping in mind that concrete is composed of cement, water, and aggregates, as well as a little bit of air that gets stuck into the material. How can we start to engineer this throughout its life cycle to mitigate impacts? And that can include things like manufacturing, making sure that we're using the right amount of cement relative to the aggregates, and maybe blending in some other components. Maybe we can improve the strength or how we're designing the members. Maybe we could start to elongate how long we use these materials through things like repurposing. And maybe we could get away with some better end-of-life management. And just to show you some initial findings that our group has recently published in Nature Communications, Here's a quick show of what we see for cement-related greenhouse gas emissions. The top solid line is, what if we don't change anything in terms of the emissions tied to cement and just keep on going the way we are with our concrete consumption out to 2100? And the answer is, we would continue to raise greenhouse gas emissions. But what about if we did manufacturing improvements, change out our raw materials, improve our energy grids? We could actually have a really substantial reduction in the emissions we tie to this class of materials. If we added on to the manufacturing and improve the mixture design, balancing out the right amount of cement to the right amount of aggregates, we can actually reduce emissions even more. And then if we pair that with improved structural design, picking the appropriate strength of the materials, we can have even further reductions in the greenhouse gas emissions. If we then tie that to improving the longevity of the system, we can have even greater reductions, so much so that with strategies that we already have available to us, we can have a 75% reduction in annual greenhouse gas emissions by 2100 for this class of materials. And ideally, re-engineer the remaining amount of materials to act as a carbon sink. So actually engineering throughout the life cycle of each of these classes of materials, looking at alternative resources to create carbon sinks, minimizing environmental impacts where we can't undo the environmental burdens, are going to be key pathways to our changing the built environment. And so with that, I want to thank, of course, the funders that have supported this work in my group, and I'm happy to take any questions that there are.
Thank you very much for your plenary presentation. Very informative, very deep and broad at the same time. I have a couple of questions. There are no questions in the live Q&A, but given all of this, the mass, the flows, the stocks, the need to expand and the need to replace, what would you say are the main drivers for materials production in terms of CO2 these days?
The main drivers for CO2 emissions currently in industrial production, we're still using a lot of coal. Okay, so first of all, there's still chemical derived emissions associated with several of our materials, as I mentioned. So the limestone decarbonation for cement, we were producing about 4 gigatons of cement annually, and the amount of limestone that we have to decarbonate in order to produce that cement leads to little under 2 gigatons on its own, right? So we're already kind of leaving a huge amount of emissions tied to just a chemical conversion. Similar things associated with steel, where we have to do direct reduction of iron ore in several cases to create the alloys that we actually want. So we do have those chemical conversions. Those are kind of sometimes referred to as difficult to decarbonize because it's actually associated with the material resource, but it's getting paired with remarkably high emitting energy resources. So some of these conversions require basically pretty high heating values, and the equipment that we have classically used that's still operational, so there's a huge capital investment to replace that equipment has leveraged fuel resources that have incredibly high emissions, with a significant amount of our coal and other fossil fuels getting used. So ideally, energy switching would be huge, but that is one of our big drivers currently.
If you were to kind of circle back to the beginning and then all of the major points you have made, how much of the current CO2 emissions could be substituted, but not through switching fuels, but perhaps switching materials? So you've mentioned that a lot of these materials are difficult to decarbonize or difficult to replace. It's a very difficult question, I know, but if you could give your best estimate as to how much of the construction materials could see alternatives scale up and how much could be replaced, and perhaps what would be the CO2 implications of that?
It is a big question. I know it's actually an area of active research right now. I've talked to several folks who've been interested in trying to understand exactly how much can we replace. So in terms of things like the bioplastics, that actually could be readily done. As Corinne mentioned, the plastics that we conventionally use in building applications don't necessarily have a perfect match for the bio alternatives, but in large, plastics kind of get cycled a little bit faster than things like concrete. So we have a little bit more potential to have a technology breakthrough there. In terms of some of our other materials like concrete, there's such slow adoption to the utilization of some of the alternative resources that it's going to be a pretty strong uphill battle. In terms of the amount of, for example, aluminosilicates that we have present on the planet, we actually could replace like 75% of our cement tomorrow if everyone would just get on board. We've got the aluminosilicates present, but actually getting that kind of, you know, buy-in from the community ends up being hard. And in terms of the aggregates, that one's going to be really tricky. We use a lot of crushed rocks, and crushed rocks are already low GHG emissions. So coming up with a way that would ideally create a carbon uptake for them, but not create huge carbon emissions for that carbon uptake, I haven't seen as much work in that area as I would like, because I think that could be really big. I realize that was a non-answer, and it's because it's so complicated. I don't have a number. I don't have a tomorrow we could replace 50%, but I think that it's kind of a little bit material specific and application specific. So for example, it's going to be harder to switch out concrete for something else in our sewer systems, but it might be easier in our frames and buildings, for example.
Well, several presentations presented several possible answers to the decarbonization problem. So it's good to hear from, you know, all corners about these things. You and others have mentioned about the reluctance, perhaps, of industry to make changes, and especially when it comes to large-scale use of materials. You know, replacing them with something that is less known is always risky. But other than that reluctance, do you see any other issues, any other obstacles to radical change in the building material space?
Yeah, so the reluctance is actually, first of all, it's sometimes tied to risk aversion. So it's not necessarily, you know, I've been doing this for 50 years, I like it. It's more of a, am I going to lose my license as a engineer if I use this material and it fails? So there could be actually some ways to get past it by ensuring how one can move past failure and have kind of a safety net associated with it. But in terms of other things that kind of could be slowing down adoption, certain new alternatives haven't actually had enough chance to be fully vetted, fully tested. So we might know that the upfront properties are fantastic. We could get this high strength, just like that I was showing on those charts. But is it going to last very long? What happens if it's under UV exposure for 5 years? Does it just disintegrate? So there's a lot of additional experimental work that could really help start to validate these types of alternative materials in some cases. Also having an appropriate sense of what resources are available where. So it's not to say that these are going to be global solutions. There's one solution that everyone on the planet should adopt, but rather what's going to be appropriate for the localized resources, what's appropriate socially, what will people feel comfortable with in that particular area, what will mitigate some of these other impacts like transportation. I think it's going to be kind of a bit of a varied answer depending on where you're physically located.
I see. So what timeline are we on? In your view, how long will this take? And how long will, you know, milestones in this process take? So do you have a sense of, and you mentioned just a couple of minutes ago that cement we have readily available replacements for and at scale. But when we're looking at true material switching actions, what do you think is the timescale? Are we talking about 5 years, 10 years? I know everybody wants to do it right now. And again, today, several ideas have been mentioned. But in your opinion, what timeline are we looking at?
So I wish I had a really optimistic, oh, it'll be 20 years, we'll be fine. But I'm not entirely sure how quickly. So I'm going to give an example of what happened in California recently that I'm hopeful will not continue to happen. But we very recently started using more Portland limestone cement in California. So effectively, we started blending in some extra materials to reduce our impacts associated with cement production. This is something that's been done in other parts of the world for decades, and we only very recently adopted it here, which makes me a little bit concerned about how quickly we'll adopt other things just as a planet. But I'm hopeful that with this increased concern and awareness that people have, and with appropriate investment, which I think is accelerating currently, both the awareness and the investment, we might be able to kind of switch our time horizons. And I know that most of the large pushes in the building material space are really shooting for the 2050 time horizon. So I'm very hopeful. I wish I had a magic clock and could look forward and answer that. But it's actually similar to the how much can we replace? Like, it's still under debate as to how quickly we could do these things and how much we actually can switch out.
I appreciate the complexity of this answer. Thank you. Last question. Mostly we talked about decarbonization today, right? So every time materials came up, energy came up, and then decarbonization came up. But what is your perspective on the co-benefits? So if we decarbonize, what else are we doing?
Yeah, I think that there could be many things that are co-benefits. So one of them could be things like particulate matter, as well as SOx and NOx, which I realize are precursors to particulate matter, but they're also precursors to things like acid rain. So I think that if we're able, first of all, to switch out these fossil fuels, we should have a reduction in some of our air pollutant emissions, which could be really beneficial to those who are locally near the industrial manufacturing, which I know in the United States have been in conventionally low income areas, which means it's already affecting a population that has disproportionate impact. So if we could fix both of those at once, that could have a huge co-benefit tied to it. We also could have co-benefits in terms of resource extraction, though. So if we're able to switch to a renewable resource, perhaps we could start to kind of limit the amount of resource scarcities that we're actually causing tied to overconsumption of non-renewable resources in any individual area. And that could actually facilitate more sustainable material production and reutilization. So I think that there's a couple of different ways. Again, it's going to be highly specific, though, depending on where you're located as to what the options are. But I think that there's, several ways that we could actually do this.
Wonderful. Thank you very much for your answers and your presentation. And since this concludes our session and the conference, I'd also like to thank all of the speakers today and thank you for doing work on sustainability in general and environmental assessment in particular on building materials. And thanks everybody for being here and those people who will enjoy these presentations in recorded format. Thanks a lot and see you at the next conference.